Here's a video where I'm going to talk through the 6 types of quadric surfaces that you should know and just kind of show you some things to look at when you're trying to identify what a quadric surface is, from a given formula and match up to pictures and stuff like that. So our first quadric surface I want to look at is an ellipsoid. And for an ellipsoid, it's going to be you're going to write it so that on the left you have all of the terms with the variables in them. And all of these terms must be quadratic, x squared, y squared, and z squared. You're not seeing just like a z or an x here. On the right you've got the constant 1. And then maybe there are other coefficients here attached to the x squared, y squared, z squared term. There's a 1/9 attached to this y squared, but the important thing is that all of the coefficients here are positive. So there could be other things. I'm not writing down the most general form here. The important thing is that the coefficients on x squared, y squared, and z squared are all positive. So here's like an ellipsoid. It's a little bit stretched in the y direction here because we've got the y squared over 9. It's going to stretch into the y squared. Sorry, I shouldn't say the y squared, just the y direction. And there's a special case, so this isn't one of our 6 types of quadric surfaces. This is a special case of the ellipsoid. It's a sphere. When you have x squared plus y squared plus z squared is equal to 1, the coefficients on x squared, y squared, and z squared are all equal to each other. Of course, we know what a sphere looks like. So then the next 2 I want to talk about are the hyperboloids. And so there's a 1-sheet hyperboloid and there's a 2-sheet hyperboloid. And so the reason I want to do these two, I should say, immediately after the ellipsoid case is that once again, these have x squared, y squared, and z squared quadratic terms and all of x, y, and z located on the left side of the equation and the constant 1 located on the right side of the equation. The difference between these hyperboloids and this ellipsoid right here is the number of minus signs. So the ellipsoid here, or just looking at a sphere here, all of our signs here are positive. All of our signs here are positive, 3 plus signs. Now we have 2 plus signs and 1 minus sign here. This gives us a 1-sheet hyperboloid. Here we have 2 minus signs and 1 plus sign. This gives us a 2-sheet hyperboloid. I like how the book kind of suggests that the number of minus signs that you see on the left side of your hyperboloid equation, the number of minus signs tells you how many sheets there are to your hyperboloid. 1 minus sign, 1 sheet. 2 minus signs, 2 sheets. Not only that, but the locations of the minus signs and the plus signs tell us which way our hyperboloid is going to be oriented. So take a look here. This one has a minus sign attached to z squared, and we can see that this is like opening onto the z-axis in some way. That this is, it's encircling the z-axis. If instead I were to change this to make it, let's say, minus x squared plus y squared plus z squared is equal to 1, this is still a 1-sheet hyperboloid. We have quadratic terms on the left, constant 1 on the right, and exactly 1 negative sign. So now this is going to be centered on the y-axis. So this picture and this picture are just the same generic shape, just rotated so this is centered on the x-axis now. If you move the minus sign to be attached to the y squared term, then it would be centered on the y-axis. Similarly, here, for the 2-sheet hyperboloid, we see that we only have 1 plus sign that's attached to z squared here, and again we see that this is centered on the z-axis. So that's not a coincidence here. If I were to draw now negative x squared plus y squared minus z squared is equal to 1. Now the only plus sign is attached to the y squared term here. And so this is going to tell me that I need to center my hyperboloid. My hyperboloid here is going to be centered on the y-axis. And if we move the plus sign to the x squared term, it would be centered on the x-axis. So these first three that we've looked at, of the ellipsoid and the sphere, the hyperboloid of one sheet and two sheets, these all have three quadratic terms on the left, maybe with minus signs in the hyperboloid cases, is equal to a constant 1 on the right. So the next one I want to take a look at here is the cone. And so this is what a cone looks like. Once again, we see there are only quadratic terms here. We don't see just a z, or we don't just see an x or a y here by itself. We see x squared, y squared, and z squared here. But now there's no constant term. Now there's no constant term. So it's of the form z squared is equal to x squared plus y squared. And so this is the shape that we get here. And so note here that z squared is equal to x squared plus y squared. This is centering the cone on the z-axis. So as a follow-up example here, if instead I said, hey, think about x squared is equal to y squared plus z squared. The fact that x squared is on the left, well, that tells us that we are going to be centering our cone on the x-axis. And it was y squared is equal to x squared plus z squared. The cone would be centered on the y-axis. Now, one little riff off of this cone, that I should just say, just because this will come up later in the course, is that sometimes you might take the square root of both sides here and just end up with like z is equal to the square root of x squared plus y squared. This is a cone. This is a cone, but it just is going to be a single cone. So in this case, z can't be negative here, and so it's just as a single cone. Okay, so the cone, like the predecessors, the ellipsoid or two hyperboloids, has only quadratic terms, but it doesn't have a constant term like the hyperboloids and the ellipsoid slash sphere. So now the last two that we're going to look at are going to have some purely linear terms in them. And so here we see elliptic paraboloid and hyperbolic paraboloid. So elliptic paraboloid is z is equal to x squared plus y squared is an example of an elliptic paraboloid. You know, these curves here are parabolas opening upwards. And the fact here that we have that it's z is equal to x squared plus y squared tells us that we are opening up onto the z-axis. So if instead we had y is equal to x squared plus z squared, that would be this paraboloid going on right here. It's opening up onto the positive y-axis. And then finally, we have a hyperbolic paraboloid, probably the trickiest one to draw here. Parabola, stuff like that. It looks right here, looks kind of like a saddle, a horse's saddle, or as we talked before, Pringles potato chip here. It's going to be z is equal to x squared minus y squared, or something like that. So there's one plus sign and one minus sign here. Of course, for all of these, you could have coefficients on them. I'm doing kind of the simplest case where all the coefficients are either plus or minus 1. You know, we could have, you know, put in 3x squared plus 4y squared. That would distort this a little bit. You know, 2x squared minus y squared would distort it, and just like in all the previous ones as well, even though like hyperboloids, you could change up the coefficients. But the really important thing here is the signs of pluses and minuses. So hopefully this sheds some light as to how to kind of match up equations to pictures.